Hello, geometry friends. Today we're going to talk about some triangle properties. The first one, and probably the most important one, is that the sum of the interior angles of any triangle is 180. You can see that I've measured these three angles in the triangle, and then I've also calculated right here the sum, which is equal to 180. And even though I can move the triangle around, and you can see that each of the individual angles are changing. What you can't see is in this measurement up here that these three individually things are changing as I move the triangle, but yet it stays constant 180. So, but I also wanted to show you another thing to kind of demonstrate this, that if I take this triangle, it's not doing it, and I rotate, let's do this. I'm going to choose the whole thing here and rotate it. Okay, that puts the yellow angle over there, the green angle goes up there, and the red angle goes down there. If I put a midpoint here, we construct a midpoint, and then I'm going to rotate all of this 180 degrees. That doesn't look like they're going to do it. Negative 180. Wait. Hold on. I have to make that the point of rotation. Now let's try and rotate it. Transform, rotate, 180 degrees. There we go. And what you can see is that I've put this triangle, rotated it here, and then again over here. And you see, we know from the original triangle that the red, the yellow, and the green triangle add up to 180. And then, but you also see right here, I've got those same three angles put together, which forms a straight line, which we all know is 180 degrees. So just a demonstration of that fact. Okay, let's move on to the next thing. We have, in a triangle, we have interior angles. I've got those same three angles I had a while ago, the yellow, the green, and the red. But then I extended the sides, which creates what's called exterior angles. And we can see that right here is an exterior angle. Okay, there's also one on the flip side that's not shown. There's one right here, an exterior angle, and there's one on the opposite vertical angles to it. There's one here and then one on the opposite side there, but I've just got those three shown. One of the things that we find out about an exterior angle, if I measure this, let's see, DBC, you can see that that's this angle here. ACB is this angle up here, 62 degrees, and CAB is this one down here at 81 degrees. And we can see that if I add 62 plus 81, it's going to be 143, which demonstrates the fact that an exterior angle is equal to the sum of the two remote interior angles. There's three interior angles. There's one that's close, that's adjacent to, and these two would be considered remote interior angles. So if I were to measure this angle over here, angle CBA, measure that angle, we see that that's 37 degrees. And so if I were looking for this angle up here, then all I would have to do is take 37 plus 81, which should be, what, 118 degrees? So that one would be 118 degrees. And then if I were looking for this exterior angle, all I would have to do is add the 37 and the 62, which would be 99 degrees. And that would be the exterior angle theorem. Now, I also want to demonstrate it a different way. If I take this angle and I rotate it 180 degrees, let's go transform, rotate. Let's see if it's still, I'll go 80 degrees, no, 180. Oops. And that would go down here. And then if I took this green one and I translated it over, then you can see that this exterior angle is equal to the red. It's got the red and the green angle in it, and there's the red and the green angle over there. And this would be true no matter what the shape of the triangle. I can still see that this exterior angle is going to be the sum of the red and the green angle over here. So, just another demonstration of the exterior angle theorem. Let's go to triangle inequalities. If you haven't seen this yet, there's a really interesting episode of Cyber Chase, episode 204, True Colors Part 2 and 3, that talks about this very thing right here called the triangle inequality theorem. And what it tells us is that a triangle, although it can be made of different side lengths, there's some limitations to it. For example, we can have a triangle where all sides are equal to 4. That would be an equilateral triangle. Okay, that's what that would look like. Now, we can have, this is isosceles because two of them are still 4. And we can extend this one out, but you notice that we get past, or we get to 8 on the bottom, that we don't have a triangle at all, because these two 4s put together would form a straight line, which is exactly on top of the straight line of side A. And then when we go past that, certainly we wouldn't have a triangle at all. And then, so just a further demonstration, I'm going to put this on 5. And so I can move this one. I can move this one bigger to a point. Let's see, we're getting close to 9. And we see that at 9, it disappears. Okay, if I go back this way and shorten it, that I get to 1, and it disappears. And if you notice that right now I'm at 1, where these two, 1 and 4, if you put those two together, again, it's going to equal to 5, so it can't be a triangle. So if this one is a little bit more, so basically what we've got to have is the two short ones have to add up to more than the longest one. So we've got right now 2.9 and 4, which would be 6.9, which is greater than 5, so we have a triangle. But then you remember when I went and took this one all the way to 9, that it disappeared. And the reason is because these two are now the shortest ones, and they add up to 9, so once I get up to 9, my triangle disappears. It can't exist. So bottom line here is take the shortest two sides, add them together, and they must be greater than the third side to form a triangle. Okay, I can make this one smaller, and when I do, since this one's the longest one, let's move this back to about 6. So just making a prediction, this is at 5. I can make this go all the way down to 1 until it disappears. Okay, and then I can go all the way up to as much as, well, I'm not going to have room. It looks like I could go up to 11 before it disappeared, because once I go up higher, the two smaller ones here, these would be the two smaller ones, and they add up to 11. So the third side's got to be less than 11. The next thing I wanted to talk about is the relationship between the side lengths and the angles of a triangle. If you look at, here's the three angles of my triangle. Right now I've got a 79, 59, 42. And then if you compare those to the side lengths of the triangle, you see that we have a scalene triangle. And if we have three different side lengths, we are inherently going to have three different angle measurements. But there's a relationship between them. Specifically, if we find our largest angle, which is this one currently at 79 degrees, and then we find our longest side, we see that it's over there. So we're going to find out that the largest angle is always going to be opposite the largest side. And then if we look for example for the smallest angle, which in this case is 42 degrees, and then we find our smallest side, and we see that it is also opposite of that one. So bottom line here is the principle is that the smallest angle is always opposite the smallest side, and the largest angle is always opposite the largest side. To extend the idea that the largest side is opposite the largest angle, if I had a situation where, in this case, I had an equilateral triangle where all three sides were congruent, since all three sides were congruent, that would mean necessarily that all three angles would have to be congruent. And so on an equilateral triangle, we know is also equiangular. If we come over here, I've constructed an isosceles triangle because we know the radii are always congruent within a circle. So if we know that the largest angle is opposite the largest side and the smallest angle is opposite the smallest side, but if we have two congruent sides, that means the two angles opposite them are going to be congruent. And these two angles are called base angles in an isosceles triangle. Okay, so this side right here is different, so this one up here is going to be different. This one up here is called the vertex angle. And so, once again, just to recap, in an equilateral triangle, we know that all the angles are equal. In an isosceles triangle, we know since it's got two congruent sides, it's going to have two congruent angles. Okay, this last one is my favorite. If we know that a right angle equals 90 degrees, and angle A is a right angle, if right angle equals 90 degrees, we could say that a wrong angle is not 90 degrees. Okay, so in this one, we like to say that in this case, two wrongs do make a right. And here's what we mean. In a triangle, we've already discussed that the sum of the three angles is 180. So if I take A, which is 90, out of that, that leaves us with 90. So if I measure angle B, and then measure angle C, we see that the sum of those two angles is 90, and since those are, A is a right angle, B and C must be wrong angles, but if you add the two wrong angles together, we get 90, which is a right angle. So therefore, two wrongs make a right. But in all seriousness, what we really mean by this is that the two acute angles of a right triangle are always complementary. So no matter what I do to change this triangle shape, as long as I've got a right angle in there, the other two angles are always going to add up to 90. Thank you for listening, and good luck on your triangle unit.